Welcome, everyone, to today's Explainer. I am absolutely thrilled to have you here because, well, we are about to dismantle a concept that you probably thought was practically set in stone. We're embarking on what I like to call the gravity voyage. Today, we're diving deep into the acceleration due to gravity, represented in physics by the lowercase letter g. Now, for most of us, gravity just feels like an absolute constant, right? You drop an apple, it falls. You jump up, you come back down. Simple. But what if I told you that this invisible force anchoring us to the ground is constantly shifting, changing, and warping depending on exactly where you are?
If you've ever taken a high school physics class, you've definitely had this number drilled into your head, 9.8 meters per second squared. It's the standard go-to textbook figure. But here's the thing, is it really exactly 9.8 everywhere you go? No way. That is the exact textbook myth we're gonna bust today. We're going to look at the hard science to discover exactly where and, more importantly, why this universally taught number completely falls apart.
Okay, let's look at our flight plan for this journey. First, we'll tackle the surface illusion. Then we'll be going up, followed by going down. After that, we'll make a pit stop at dead center. And finally, we'll wrap things up with the cosmic jump.
Stop number 1, the surface illusion, focusing on Earth's equatorial bulge.
Okay, before we actually look at the Earth's shape, we really need to understand the engine under the hood here. The fundamental formula for the acceleration due to gravity is G equals capital G times m, all divided by r squared. G is just the universal gravitational constant, and m is the mass of the Earth. But the real star of the show today? That's the denominator right there, r, the radius of the Earth. Because r is squared and sitting at the bottom of that fraction, gravity is inversely proportional to the square of the radius. In plain English, if the radius gets bigger, gravity gets weaker. If the radius gets smaller, gravity gets stronger. Keep that rule in your back pocket, because any change to the Earth's radius directly impacts the gravitational pull you physically feel.
And this right here is exactly why that formula is an absolute game changer. You see, the Earth is not a perfect sphere, not at all. Because it's continuously spinning on its axis, it actually bulges outward at the equator and flattens out at the poles. It's kind of squashed. Because of this, the radius of the Earth is highly variable. Think about it. If you stand at the North or South Pole, you are physically closer to the center of the Earth, so the radius is at its minimum. And just like our formula told us, a smaller radius means gravity is at its maximum, 9.832 meters per second squared. But if you travel down to the equator, you're standing on that bulge. The radius is at its maximum. You are further from the center, so gravity drops to its lowest point, 9.78 meters per second squared. Your actual weight literally changes just by taking a trip across the globe.
All right, part 2, going up. Let's talk about gravity at altitude. We've seen what happens on the surface. Now let's aim for the sky. So what happens as an object moves high above the Earth? Well, we have to update our math a bit. The total distance from the center of the Earth, let's just call it lowercase r, now equals the Earth's radius, capital R, plus our new height or altitude, represented by h. The logic here is super straightforward. By adding altitude, our radius gets larger. The denominator grows. Therefore, gravity's grip on you has to decrease. But the real question is, how much does it actually decrease? Let's put this into real-world perspective. Down on the surface, where height is 0, gravity is our old familiar friend, 9.8. Now let's say you climb Mount Everest, standing 8.8 kilometers in the air. Gravity? Still 9.8. Even if you take a record-breaking balloon up to 36.6 kilometers, gravity only dips slightly to 9.77. Why is that? Well, because compared to the Earth's massive 6,400-kilometer radius, these heights are practically nothing. The math barely notices them. However, look at the really big jumps. A weather satellite orbiting at 400 kilometers, that experiences a noticeable drop down to 8.7. And what about a communication satellite way out at 35,700 kilometers? It experiences a massive drop in gravity, plummeting all the way down to a mere 0.225 meters per second squared. Moving right along to part 3, going down. Gravity at depth. Buckle up, because as we start digging down into the Earth, things get a little weird. We run into a counterintuitive physical paradox. Think back to that formula one more time. If we go deep inside the Earth, our distance to the center decreases. Now, a smaller radius normally means gravity should get stronger, right? Actually, scratch that. It decreases. Why? It's all because of this really fascinating dual action mechanism. Step 1, yes, the distance to the center decreases. But here's step 2. As you dig deeper, the outer shell of the Earth is now physically above you. It's no longer pulling you down toward the center. The actual core mass, that M in our formula, that is encapsulating you and pulling you downward, is actively shrinking. And step 3 is how we resolve the paradox. This reduction in mass completely overpowers the reduction in radius. So surprisingly, the net value of gravity continually drops as you go deeper underground.
Which naturally brings up a pretty wild analytical question. If there is suddenly a whole bunch of Earth mass above you, below you, and all around you as you descend into a mine shaft, does the actual direction of the gravitational force change? Like, are you suddenly being pulled sideways? The answer is a definitive absolute no. Despite all the incredibly complex math happening as the outer spherical shells of the Earth effectively cancel each other out, the net gravitational pull remains perfectly consistent. No matter how deep you dig your tunnel, gravity always pulls straight toward the absolute center of mass of the Earth. It remains perfectly directed vertically downwards. Which brings us to part 4, dead center, zero gravity. Let's head to the very core of the planet for what is easily the ultimate mathematical plot twist of this explainer. Imagine for a second that you could somehow survive the completely unimaginable pressure and heat, and you arrived at the exact absolute dead center of the Earth. The acceleration due to gravity right there, it is exactly 0 meters per second squared. Literally 0. So how on earth, pun intended, is this possible when you literally have the entire mass of a planet pressing in around you? Well, that's exactly the secret. It all comes down to the beautiful structural symmetry of the core. When you hit dead center, the mass contributing to a downward pull becomes effectively 0. Why? Because the entire mass of the Earth is surrounding you equally in every single possible direction. The mass to your left pulls you left, the mass to your right pulls you right, the mass above pulls up, and they all perfectly cancel out each other's mutual gravitational forces. You would be entirely 100% weightless, floating at the center of the Earth. And finally, part 5, the cosmic jump. Moon gravity. Let's blast off from Earth entirely and use our own moon as a comparative case study. Every single planet, moon, and satellite floating out there in the cosmos features a completely unique mass and a completely unique radius. And as we've learned today, those are the exact 2 ingredients that dictate surface acceleration. When we compare the Earth's average 9.8 meters per second squared to the moon, we see a really drastic difference. Because it has such a small mass and a small radius, the moon's gravity sits at roughly 1.63 meters per second squared. That is just about 1/6 of the gravity we experience here at home. So what does this math actually mean for you practically? Well, if you were wearing a spacesuit, stepped onto the lunar surface, and applied the exact same muscular force in your legs that you used to jump here on Earth, the downward acceleration fighting against you is 6 times weaker. The result? You would literally soar through the air. You'd jump an incredible 6 times higher on the moon than you ever could on Earth. It is just a perfect, fun, real-world application of the physics we've been unpacking today. So we've seen how gravity isn't just some boring, static number. It's a dynamic, ever-changing force, shifting with the Earth's equatorial bulge, weakening as we climb up to the satellites, dropping in paradoxical ways as we dig down to the core, and changing entirely when we step foot on a new celestial body. So I want to leave you with this final thought. Knowing exactly how mass and radius alter the physical rules of gravity, what would your jumping height be on the other planets in our solar system? Seriously, think about it. How high could you jump on Mars? What about Jupiter? Use the formulas we learned today, and you can unlock the physics of the entire cosmos. Thank you so much for joining me on this explainer, and keep exploring.